Okay, in chapter 7, we're studying exponential functions and logarithmic functions. We're going to start in 7.1 studying what the key features of an exponential function is or are. And then we'll go and look at exponential growth and decay models. An exponential function is any function of the form y equals a times b to the x, where a and b are constants with a not equal to 0, b bigger than 1, and b is not equal to 1. So this is an exponential function. It looks just like this. Notice the x is in the exponent. So let's look at the graph first, the graph of y equals a times b to the x. So in example 1, they give you a chart and they say, here are your x values, and here is f of x. F of x equals 2 to the power of x. So we'll start f of negative 2 equals 2 to the negative 2 power. However, we cannot have negative exponents. So in order to get rid of a negative exponent, we take the reciprocal of this. So the reciprocal of 2 to the negative 2 is 1 over 2, and now it becomes a positive 2 in the exponent. So taking the reciprocal makes your exponent positive or negative. So in this case, it makes it positive because our exponent was negative. So 1 over 2 to the power of 2, 2 to the power of 2 is 4. So this is 1 over 4, which is 0.25. Negative 1, so f of negative 1 is 2 to the negative 1. Again, we had to take the reciprocal since this is a negative exponent. So this is 1 over 2 to the first, which is 1 over 2, which is 0.5. 0, so f of 0 equals 2 to the 0. Remember, anything raised to the 0 power equals 1. So 2 to the 0 is 1. 1, so we're going to do f of 1 equals 2 to the first, which is 2. And then 2, f of 2 equals 2 squared, which is 4. So then we're going to go ahead and plot these points on our graph over here. So negative 2, comma 0.25, negative 1, 0.5, 0, 1, 1, 2, and 2, 4. Notice it starts going a little faster beyond after you get past 0 there. So it's starting to go really fast here. So this is what your graph would look like. Notice it never really touches the x-axis, so your y value never really gets quite to 0, but it's going to approach 0. So what we're going to say, our domain, we're free to use as much of the x-axis as we want. So our domain, we call that all real numbers, and we denote that with this fancy little r. So that means all real numbers. The range, how much of the y-axis do we use? I already said that, is we don't ever really quite get to when y equals 0. So our range is y such that y is bigger than 0. We don't have anything less than 0 or equal to 0 on our graph for the y-axis. Our y-intercept, where does this graph hit the y-axis? Let's just take a look. It hits at the x-axis at the point 0, 1, or if you want, you could just say 1. So this is what the graph of an exponential function would look like. Some important notes about this graph of an exponential function. So I'll put some stars around that because this is important. For f, b equals 2. So this is our base. If we look at, this is our b value. If we look at the formula of the exponential, which is y equals a times b to the x. Our b value is 2. Since b is bigger than 1, the y values of the function increase. So that b value tells you whether your function is increasing or decreasing. For y equals a times b to the x, the value of a is the y-intercept. Notice in example 1, there was no a value written. That means we're just going to assume a is 1. So when I plugged in x equals 0, my function equaled 1 at that point. So 2 to the 0 was 1. Another point to make here is if b is bigger than 1, or sorry, if b is less than 1, then the y values of the function will decrease. So if b is less than 1, then the y values of the function will decrease. The most common application of the exponential function is the exponential growth and decay models. Exponential growth and decay functions model quantities that increase or decrease by a fixed percentage during each time period. Given an initial amount A and the rate of increase or decrease R, the amount A of t after t time periods is given by, so there's one or two options here. You can either have exponential growth or you could have exponential decay. If you have exponential growth, we'll work with that one first, you would have A of t equals A, little a, times 1 plus R to the power of t, where A is bigger than 0, B is bigger than 1, and B equals 1 plus R. If you have exponential decay, very similar. You have A of t equals A times 1 minus R to the power of t, where A is bigger than 0, B is in between 0 and 1, and B equals 1 minus R. The growth or decay factor is equal to B and is the ratio between two consecutive y values. So B, this 1 minus R and 1 plus R, those are your decay factors. Those are your B values. So let's look at an example. It says a car was purchased for $24,000. The function y equals 24 times 0.8 to the power of x can be used to model the value of the car in thousands of dollars, x year after it was purchased. So A, does the function represent exponential growth or exponential decay? So you would want to identify your B value first. So in this case, let's identify B. So B is 0.8 because it's the number that your exponent, your 0.8 is your base and x is your exponent. So that's your B. So B is 0.8. 0.8 is in between 0 and 1. So this function would represent 0.8 is less than 1. So this would represent decay. So B is 0.8, and 0.8 is less than 1, so this represents decay. What is the rate of decay for this function? Or in other words, what's the decay factor? So the rate of decay, so we're going to do, since this is decay, we're going to calculate our decay factor, which is equal to B. So our decay factor is our B. So 0.8, so our B equals 1 minus R, since this is decay. So 0.8 equals 1 minus R. So we're left with solving this for R. So if you subtract 1 for both sides, you get negative 0.2 equals negative R. So negative R equals negative 0.2. Divide both sides by negative 1, so this is R equals 0.2. So your rate of decay is 0.2 or 20%. So your rate of decay and your decay factor aren't necessarily the same thing.
You need to use, this really should say hint. You need to use the decay factor to determine your rate of decay. And your decay factor was 0.8 in this case. So if you could just make that one little adjustment on your notes. So we're going to go ahead and they want us to graph the function on a reasonable domain. What does the y-intercept represent? So if we graph this, I already put it in here, so this is 24 times 0.8 to the power of x. And we choose a nice table, so on this calculator it's pretty easy to put a table. Just looking at the problem, I'm going to use my x min is 0 and my x max is 10. That seems like a reasonable domain because x represents years. And we can adjust if needed. The y minimum, again, is at a reasonable domain, so anything bigger than or equal to 0 would work for y. So I'll have y, and then y max, I'll go 30, and my scale is 5. So, and this is 30, remember your y represents 30 in thousands of dollars. So that would be like $30,000. Let's go ahead and graph it. If you do, this is what you get. So they want us to go ahead and sketch this. So this would be, I'll just sketch that out. Just looking at the calculator. So up, so this is 5, 10, 15, 20, 25. And so this is your value in thousands of dollars. So the y-axis represents the value in thousands of dollars. The x represents your time in years. So let's just do 1, 2, 3, 5, 6, 7. Let's go up to 8. And if we need to go further, we could. So it looks like this graph hits the y-axis just below 25,000. So when time is 0, when the car is purchased, the car is worth all it could be. So it's worth 24,000. So at 0, this is 24,000. And then the graph, if you just sort of look at it, or just a swoop, sort of sketch it like that. Definitely should look exponential since this is like an exponential equation. So mine's not quite, doesn't got quite the correct steepness, but that's okay. So they want to know, what does the y-intercept represent? So the y-intercept represents the value of the car when it was purchased. Because the y-axis represents the value of the car. So when time is 0, that's the time when you're purchasing the vehicle. Part D, they ask you to use the graph to determine when the function, when the value of the car will be about $5,000. So if we look at the graph, so let's just go ahead and use our graph here. We can use this feature that allows us to trace, actually, we'll just look at the table. So if you look at the table of the graph, we want to see when the value of the car is about $5,000. So at 0, we're at $24,000. At 1, we're at $19,000. So if you keep going, at 4, we're at $9,000. So we keep going until we get close to 5. So it looks like at about 7 years, you get pretty close to the $5,000 mark. At 8 years, you're well below 5,000. So we'll say that when X is approximately 7 years, Y is approximately $5,000. So when X is about 7 years, Y is about $5,000. Example 3, the population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over that 4-year period? So there's some things that we need to determine before we can even write our function. We need to determine, first we need to determine what is our rate. So at what rate is this growing over these 4 years? And that's going to be the percentage. So it tells you at a rate of 1.3%. So 1.3% as a decimal, in other words, do 1.3 divided by 100, that is going to be 0.013. So that's our rate as a decimal. So 1.3% as a decimal is 0.013. Next thing we should probably know is, what is the initial amount? So our initial amount is 4.6, and we'll put in millions of dollars. That way we don't have to put all those zeros. So our equation, if we think of the exponential model, y equals a times b to the x. Well, what is y? We don't know what y is, so we're going to say y equals, a represents your initial amount. So this is your initial. And b will represent your growth or decay factor. So your initial amount here is 4.6 million times your growth factor. So if we go back to that page, last page, so remember your growth factor is 1 plus r, since we have growth. So this will be 1 plus r. So what is r? R is your rate. So this is going to be 1 plus your rate, which is 0.013 to the x power. So that would be our function, and we could clean this up. This would mean that y equals 4.6 times 1.013 raised to the x power. And they want to know, so that would be your function to model this situation. In part B, if the population grew at the same rate, what would the population be in 2040? So how many years in between 2010 and 2040? Well, that's 30 years. So you would do y equals 4.6, and this is all in millions of dollars. Or sorry, in millions of people, sorry. So 4.6 times 1.013 raised to the 30th power. If you do that in your calculator, y equals 4.6 times 1.013 raised to the 30th power, you get y is approximately 6.78 million. Sorry, I made a mistake up here. This is millions of people, not dollars. Hopefully you caught that. So y is approximately 6.78 million people, not dollars. So as long as this population keeps growing at the same rate, this function could be used to determine what the population is going to be in the future.